Right, welcome back, everyone. Uh, kind of quiet day today. People are depressed. I don't know. We are in week 6. So we starting last lecture, we kind of start to pivoting from processor and start talking about memory. And few things to remind you about the homework and the computer assignment. We also released a rubric for quiz 1, and we started grading it. Hopefully, it should be out soon. And as I said, don't be too stressed out about your grades and all. Typically, at least my experience in the past few offerings of this course is that since the grade is kind of like very distributed in multiple components, there's always like things average out. So if you miss one particular component, there's always ways to compensate for that. And then you also have opportunity to look into the rubric, and when the grades are released, ask questions. Make sure that you understand the rubric correctly. We're going to follow that exactly, so don't try to kind of, I mean, lots of people I see that being opportunistic about getting more points, but typically we ask the readers to be kind of very strict about what can be done and what cannot be done so that we maintain some consistency. But of course, there is possibilities of errors. So you're more than welcome to look into your grades and the way that's been graded and ask for regrade requests if you believe that there has been a mistake. As I said, the grades hasn't been released yet. Maybe next week, I don't know. I cannot promise. It's in the hands of the readers. So whenever they're finished, we're gonna release them. Any questions? And of course, the elephant in the room is the election. So I'm sure that you guys have their own opinions. You might be sad or happy. And usually STEM classes doesn't really talk about this. I'm not an expert, so I'm not gonna talk much about it as well, but I just, as a suggestion, hope that you keep the conversation civil, right? So one thing that I always intrigued about tech in general and sciences is that you can have a very civil discussion on, let's say, how to design a branch predictor, right? And you can have disagreements, but there is a very, very clear way to prove that this design is better than the other design. But then when it comes to other topics, unfortunately, that's not the case. And I think what is lacking is the same framework, right? So if you can actually apply the same framework that you do for something like designing a branch predictor to talk about, I don't know, policy and politics and all, hopefully the discussion would be a little bit better. So I'm hoping that you kind of apply this kind of a skill set that you have, an engineering skill set, in your humanities as well. But of course, there has been lots of research and all on the humanities side, so hopefully you can get that to work. And then another thing that I want to say is I noticed after many years in academia that people are in their own bubbles. And I think sometimes media kind of advertises as like people outside colleges and universities are in bubble, and people inside the university are these elites that know everything. But what I realize is actually it's both ways, so that people in academia is in their own bubble. So try to come out of that bubble and understand that there are different views in the world. And just because we have PhD degrees and going to good colleges and I don't know, earn lots of money and all, doesn't mean that we are right at every single decision that we make. And there's only one way of, there's one value system, there's one way of thinking. There are many ways of thinking, all of which are useful and important. So try to expand that as well. Okay? Anyway, so let's talk about caches. That's what we are here for. So last time, if you remember, I told you that we want to have memory hierarchy to call me that, ask me not to talk about this. Hello. Oh. We got advertised. Wow. So it's it was a scam call. Anyway, so if you remember, I told you that I want to be able to cache things because I want to have a memory that is have this illusion of large, but fast. And the first thing that we introduce is having some smaller kind of memory closer to the CPU, and this way I can put things here that I need most, and this is much faster than going through the memory to layer 2 or layer 3. Um, and this is the idea of a cache, okay? For now, we're going to talk about just one level of cache. And as I said, we usually divide it to an instruction cache and the data cache. Um, but later on, you're going to see that the cache itself can have multiple levels, okay? Um, and then when we're designing the cache, the main thing about the cache is how fast can we bring the data. And as I said, since this is a whole system of multiple levels, uh, at the end of the day, what is really matter from the CPU perspective is that how long does it take for me to access a particular data. I don't care which level it hits and where it's coming from. Only thing I see is this delay, right? And we call that the average access time. Of course, this is an average number because different values might be stored at different places, so their access time might be different. And then we showed you that there are three main metric or three main kind of factors that is important for the average access time. The first time is hit time, which means that how long does it take for us to search the cache, and hopefully it's there. If it's not there, that would be contributing as what we call miss rate. You want the miss rate as low as possible. And then if there are some cases that the data will not be in the cache, then we have what we call the miss penalty, which means that how long does it take for us to go and grab the data from the lower level. And as you're going to see later, we're going to see that this miss penalty itself is a combination of a bunch of numbers because we have multiple levels, and the miss penalty varies depending on where we're going to go and grab this data, okay? So it's not going to be just one number. For now, since we only have a cache and a memory, there's only one number. But later on, you're going to see that this is actually a summation of a bunch of different numbers, okay? And then we start talking about how do we design our cache. Like, now I know that I want to minimize this average access time. How do I do that? And the main problem that I'm going to have is that I have limited space. Of course, if I had all the space in the world, I will just put everything in the cache and call it a day, right? But the problem is that I don't have that, so I need to have some form of a management. I need to have some form of strategy to decide what to store and when to get rid of it and when you replace it with the other things and so on and so forth. So the whole kind of data management of what to place in the cache and what not to store in the cache, that's the story of what we call cache management, okay? So this is what we're going to talk about in this lecture and as a main part of this lecture, okay? The first thing that we need to do is that we need to search the cache, right? So that's like regardless of what we store, we need to have a mechanism to know whether that data exists in the cache or not. And as I said, in addition to the data, obviously, that you need to store, you also need to store the tag. Why do I need to do that? The reason for this is this, right? So that since the cache is a smaller entity than your main memory, there are going to be addresses in the memory that map into the same address in the cache. So for example, in this picture that I'm showing you here, all these gray boxes or gray kind of blocks going to all be mapped into the same gray block in the cache, okay? Since now for every given block in the cache, there are multiple options to store, I need to have some form of an identifier, right? I need to be able to not only say that, okay, this is the value that I store, but I also need to say that for which address this value is stored there, okay? And the same story for the blue block here and the other blocks, okay? So for example, I can start with this like very simple strategy that I assign numbers to each block. Say that, okay, this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, 6, 7, 8, 9, and so on and so forth. So what I'm going to store here is that not only I store this value here, I also store, like I add an additional column here, and I store the tag. So for example, if I store this guy, I'm going to store 1. If I store this one, I'm going to store 9, and so on and so forth. So when I see the cache, the first thing I check is what is the tag, right? And I see, for example, the tag is 9, which means that I stored the memory that is mapped to 9, okay? So now the question is, how do I assign those tags and all that I'm going to explain in the next few slides. But generally, the idea is that I need some form of an identifier for each line that I have, because the data itself not going to be the identifier, right? So the data could be any number. So I need an additional identifier for that. We call that a tag, okay? So what I'm going to actually have in a cache is not just the data store, so it's not just the memory and the values, but also another storage mechanism called the tag store, okay? And when an address from the CPU side comes, what I need to do is that I need to check both of these, right? The tag needs to basically tell us that whether or not this data is there. So this is basically decide whether this is a hit or a miss. If it is a hit, then we need the data. If it's a miss, then it doesn't matter what I'm storing here, because the data that I want is not going to be there. I need to go to a lower level caches or the memory and bring that data, okay? So keep that in mind, that kind of the process of searching for the cache and deciding whether it's hits or miss is a two-step process, which the first step is checking for the existence of the data, not the value, the existence of the data. If it's there, then we're going to have hit or miss. If it's there, we're going to have hit. And if it's not there, it's going to be miss. If it's there, if it's a hit, then we're going to actually go and grab the data. If it's a miss, then there is no point because the data is not there, okay? So how do we store the tag, and what should we store? So let's just start with a simple example, and then we're going to actually make it to a realistic system, okay? Let's say that I have addresses that are just 3-bit, okay? And then if I have 3-bit address, it means that my main memory is going to be 2 to the power of 3 or 8 different blocks, right? So 8 different bytes. So for example, I'm going to have 0, 0, 0, 0, 1, 0, 1, 0, and so on and so forth. And this would be the data that is stored. For example, block number 0 has A, block number 2 has B. These are just values, okay, some random values. So if I have a cache that is as big as of a memory, then I can have one-to-one mapping. I don't need to store anything. I'll just store everything that I have. And I said, in this case, my cache and my memory would be the same size. In reality, this is impossible, because if I had the biggest cache, then there would be no need for the memory. And I already told you that we have kind of limited by the technology. I cannot have a big cache. I can only have hundreds of kilobytes of cache, unfortunately. But in reality, I need terabytes of data, okay? So let's say that, for example, I have a cache that is half the size of my memory. Again, I'm just making arbitrary assumptions here. So this is my main memory, and this is my cache, okay? So my cache is half the size of my memory, okay? And let's say my addresses in the cache, of course, it would be 0, 0, 0, 1, 1, 0, and 1, 1, okay? So now the idea is, what do I store here as a tag? And of course, I need to also store the data. So what should I store in the cache? What are the options that I have? Anyone wants to suggest? Yeah. Yeah, so for example, in this particular case, seems to be fairly straightforward. I just store the most significant bit, and that would be enough, right? So basically what I will do is that I'm going to follow this format, right? So I'm going to use the lower 2 bits as my quote-unquote index. And since I have this, the only remaining bit is this most significant bit. So if I store this 0 here or 1, 0 or 1, then I know that whether I'm storing this or I'm storing this, right? These are the 2 lines in my memory that the lower 2 bits are the same. So they're both mapping to the 0, 0. And in order to distinguish between the 2, I just stored the most significant bit. So when I want to search, so for example, an address comes, all I need to check is that I use the first 2 bits of the address as my index. I'm going to go through that lines, so I have 4 different lines, right? I'm going to use the first 2 bits of the address to select one of these 4, and then I'm going to check the bits that I stored here. If it's 0, then the address would be this. If it's 1, the address would be this. So whatever these 2 bits are, right? And you already seen this in our BTB, basically, right? So in BTB, we also did the same. So in your homework, you probably have seen this format of storing the tag. There we store the PC. Here we are storing the memory address. But the idea is exactly the same, okay? So as I said, this is exactly what I'm doing. I'm using the lower 2 bits for my index. And then I'm using that one single bit as my tag store. And you will see that my tag store is essentially 4 rows, and each row is only storing 1 bit, right? So it's a 4 by 1 array or a matrix, whatever you want to call it, okay? And then as you can see, in this case, that my address was 3 bits, you can essentially divide the address into 2 parts, the index and the tag. So in this particular case, I have 2 bits of index, and I have 1 bit of tag. And the reason for it is that I gave you this initial assumption that I have 4 lines, right? So now, for example, if I told you that instead of 4, I had 2, only 2 lines in my cache, then this would have changed to 1 bit of index, and then the remaining bits would be tagged. So in that case, it would have been 2 bits of tag, right? So I need to store 2 bits per tag, but I only have 2 different rows. So it would be a 2 by 2 in that case, right? So slightly different types of memory that I'm going to have there, okay? Uh, is that clear? Any questions here? Perfect. And remember, we still need to store the data, okay? So your cache, as I said, is this 2-unit thing. That one is what we call the tag store, and the other one is what we call data store. And as you can see, for example, if the data that I'm storing here is A or B or C, what I'm really having is that my cache is this, okay? So I'm storing whatever here and then the corresponding data in my data store, okay? So at any given point, I have 4 different values stored in my cache in this particular system, okay? And then what I do is that I first check the tag to see if that data that I want is there or not. And then if it's there, I'm going to go and grab it from the data store, right? So as I said, this is essentially the way that we do the mapping, okay? But now the question is this the only way of mapping the data? Is this the best and only way of mapping the data? Or are there other ways that I can also map the data? So we're going to talk a little bit about alternative ways of mapping the data into the cache. Yeah. Yeah, good question. So, okay. So the question is that in this case, I can never store both A and E. And the answer is yes, you can't, unfortunately. You cannot store both A and E at the same time. We call this conflicting addresses. So A and E always conflicting. Uh, for example, how do I fix that? If I had a bigger cache or if I had a different mapping strategy, then I could have stored both A and E. And that's actually the motivation for us to consider other types of mapping uh, or having a bigger cache. Okay, something happens to my Zoom. Uh, sorry about that. Okay, back on. Start. Okay. Yep. Okay, sorry about that. But yeah, very good question, actually. Okay, so let's actually talk about that, like how we can do a different mapping and why it matters and why we can make things better, okay? Uh, so I'm going to talk about this. Uh, so there are two ways that comes to the mind. There are two very simple ways. The first one is what I said, that I have this kind of indexing that I know the address, I go straight to that index, okay? And that's one way of doing things. The other very intuitive way of doing this is kind of a free-for-all situation, that we don't assign anything to anything. We just grab the first available spot and then put it there, okay? So for example, going back to this idea here, I'm not going to have the notion of index, okay? There's no index. Everything is just tag, okay? So all the 3 bits is tag. What I'm going to do is that I'm going to store the whole address here, but then any line can be assigned to any line, okay? And think about the seats of in this class, right? When you come to the class, you can choose, you can sit anywhere. And if I want to say, for example, where Joseph is sitting, I need to basically search through the whole, class and find him there, okay? The alternative way would have been that I assign, let's say, for example, row and seed ID based on your UID and say that, okay, if you're an odd, if your UID ends with an odd number, you can only sit in the odd numbers. If your UID ends with an even number, you can sit in even numbers and so on and so forth. That means that then I can only, I can check your UID, I can check the rows, and I can find you, right? Or for example, if you go to a concert, there's actual number, right? So row 6, seats number 2, and that's exactly where you sit, so I can know exactly where you are. But the trade-off between these, different options is that, depending on which one we're going to use, there are two problems, right? So the problem for this kind of like straightforward approach is that I'm not going to use my my space the most efficient way. Because, for example, let's assume that I only have 2 addresses that are always conflicting, okay? So for example, going back to this example here, if the only addresses that I really care about is A and E and A and E, what's going to happen is that I'm going to store A, then E comes, and E wants to be stored in the cache, so it has to kick out A, which we call evict. So it evicts A and replace it with E. Then A comes and evict E, and then E comes and evict A. So we kind of like have this kind of ping-pong-based approach here that although I have 3 other lines in my cache that can be used, and I can simultaneously store both A and E, I don't because they all happen to just map into the same address, okay? But the nice thing about this index-based approach is that it's very fast. I can know exactly. I see the address. I know that this is either it's in that 0, 0 line or it's not there at all. I don't need to search the rest of my cache to see whether A or E exists. I just see the address. I go to one block and one block only, and I'll find it or don't find it, right? That's all. Versus the other option is what we call the fully associative option, is that I'm just letting the data to decide where they want to sit. We just find the first empty spot, and we're going to put the data there. In that case, then I can safely store both A and E, which is great. So in terms of utilization, this is fantastic. In terms of cache hits, I'm going to get the most cache hits. But in order to search, I have no idea where this data is stored. So I generally need to search the entire cache to find it. For folks that know the big O notation, tell me what is the complexity for searching the first versus the second. Let's say I have n different lines of memory. Yeah. Yeah, exactly. So I'm going to have O of 1 versus O of n, right? So if I have bigger cache, it's linear with the cache, right? I have to search through the entire cache. The complexity of this algorithm scales with the size of my cache, which is not great because in real cache, we're going to have thousands and thousands of lines. Versus in what we call a direct mapped approach, it's O of 1. So it doesn't matter how large is your cache, your hit time is always the same number. Okay, so that's the difference. So this is kind of like the the trade-offs that we are facing. That we have what we call the direct map cache, which we have the index to assign everything to one and one index. This is the example that I gave you. Or we're going to have uh, 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 the other option, which is what we call a fully associative cache, right? That we don't care about the indices. We just store everything into the cache, right? So we have the full thing as the tag. So my tag store now needs to be bigger. But this gives me much better utilization, and we call this fully associative, okay? Which means that we are using the whole thing. So I have what we call direct map versus fully associative, okay? There are a few other things that I want to say before jumping into the kind of comparison between the two, and that is the lookup, okay? So as you can see in the direct map, the way that we're going to do this is we essentially going to take the index. Based on the index, I'm going to select one of the rows. So for example, let's say in this case, I have an 8-bit address, okay? And I have 8 rows. So as a result, I have log 2 of 8, which is equal to 3. So I have 3 bits of index, okay? And then since I have 8-bit address, 8 minus 3 equal to 5 is the number of tags, okay? So this is how I'm going to compute this. So if I ask you that, compute the size of the tag and index, you have to first see which sort of mapping do we have. Do we have a direct map or a fully associative? Then I'm going to see how many rows I have in the cache. So for example, I'll tell you that you have 16 rows. So log 2 of that is the number of bits you need for the index. In this case, you have 8 different rows. So log 2 of that, you're going to have the number of bits you need for the indexing, which is 3. Then since the whole address usually is 32, but for example, in this case, I'm telling you that it's 8 bits, just arbitrary numbers. Whatever remains will be your tag, right? So in this case, it would be 5 bits, okay? So I'm going to have and then of course, you're going to have a data store, which is the size of your data store is kind of depends on the number of rows that you have and the size that you store in each row. Usually, you store 1 byte, okay? So it means that if I have 8 rows, I'm going to have 8 times 1 byte. I'm going to have 8 bytes of data store. So this would be the size of your data store. You can also compute the size of your tag store, okay? All right, so in order to kind of what we call cache lookup, which means that how do we search the cache, what we're going to do is that we're going to first search through use the index to select the line that we want to use. Remember, this is direct map, which means that I know exactly the data should be. So for example, in this case, let's say it's 111, so I'll select this last one. Typically in tag store, we also have a column called valid bit. The valid bit tells you whether you actually store something there or the data is there is invalid. So it means that you don't have to even search, okay? If the valid bit is there, then I'm going to read the tag that I stored there. In this case, it's a 3-bit value. I'm going to check that, 5-bit value. And I'm going to check that tag with the tag as coming from the address from the CPU. So this number is coming from the CPU side, right? So this is the memory address on that load word instruction that we have, right? So that's the address. As I said, in RISC-V, we learned that that's like a 32-bit number, but as I said, this is just an arbitrary assumption here that it's an 8-bit number, okay? So don't be confused about that. So it's an 8-bit number. I check the tag. This 5-bit with 5-bit. If the answer to this is yes, that means that these two numbers are matched. We're going to say it's a hit, okay? If it's a hit, then I'm going to also go to the data store and bring the data. So as I said, for example, if I store 1 byte, I'm going to provide 1 byte of data. So this is the actual value that memory load word value is going to forward back to the processor. So remember, we had load word, and we had like something like x2, I don't know, 4x0. So this is data that's going to be written into x2. And remember, we had SB and SW and SH, which was half word. So how many bytes we're going to read, we're going to be dependent on that. For now, let's assume that everything is 1 byte. So I need to repeat this process 4 times to read the whole 4 bytes, okay? So this would be the value that I'm going to read. But this is what we call the cache lookup, okay? So let's check the tag first. If the data is there, we're going to check the data. Questions? Yeah. Yes. So the comment was, we use the index, we select the row, we read the tag, we check the tag that is stored versus the tag that we have on that address. If they match, it's a hit. Great. So one thing that we do is that we typically do this in parallel, okay? Which means that, well, in reality, I need to first check whether the tag is matched or not, okay? And then read the data. But that means that this delays is serialized, which means that I have to wait for the tag checking to finish before I can read the data. What I do is that I read the data here, and I read the hit and miss. And what I do is that basically, think about it this way, that I'm going to have some form of a mux that if it's a hit, I'm going to select this, okay? So this is coming from the data store. If it's not a hit, if it's a miss, then I need to forward something else. And that something else is typically coming from the lower level of memory, right? So for example, here, either I'm going to send 0 or something like that, or bring it from the memory. But essentially, the idea is that I don't wait for the tag checking to finish before reading the data. I do this both in parallel and then have a multiplexer to select which one to select, okay? So keep that in mind as well. All right. So as I said, the alternative to the direct map is what we call fully associative, right? And in fully associative, what we're going to have is that there's nothing called index at all. Everything is just tag, right? So I'm going to have the 3 bits, for example, going back to that 3-bit. All of these 3 bits going to be stored in the tag. But the nice thing is that each line can be mapped to any line. So line number 0 can be mapped to this one, this one, this one, or this one, okay? And then as a result, its corresponding data can be stored in any of those, okay? All right, so let's actually give you an example. Hello. Insurance marketplace. All right. So we have if I want to show you the kind of the cache, how the cache would look like in a direct map versus in a fully associative, basically this is what we're gonna have. All right. In a direct map, I'm gonna have basically 4 different lines, and as I said, typically these 3 are together. It's called tag store, and this is called data store. Here I combine them so that you can see them all together. In direct map, I'm going to have usually a valid bit. This is just one bit. Then I'm going to have the index, and this index could be depending on how many bits that how many rows that I have. For example, in this case, I have 8 different rows. As a result, my number is going to be from 0 to 7, 3-bit data. Then I'm going to have tag. The tag here would be much smaller than the tag that I'm going to have in the fully associative, because here the tag is whatever address that I have minus the number of index, the bits that I need for index, versus here is the full address, right? So here is bits in address minus index. Here is the full address, okay, and the number of bits in address. For example, in this particular case that I have 8-bit data and 8 rows, if I want to calculate these things, I'll see that index is, for direct map, my index will be log 2 of 8, which is 3. And my tag will be the number of bits in the address minus the index That's the number of bits that I have. This is for my direct map. For my fully associative, index is 0. I don't have any index ever. And my tag would be basically address, which in this case is 8. Okay? So that's the difference. So the tag store in a fully associative cache is much bigger than the tag store in the direct map cache. But both of them had the exact same data store, okay? So the data store has nothing to do with the strategy that you're using. It's based on the number of rows that you have in your cache, okay? So you can then compute the tag size, right? So you can see that the tag size for direct map versus fully associative, how does it change? Let's actually also talk about the access pattern and see why the access pattern is important and how these two are different. Question. The question is, are we storing the index in the direct map to no? So the index is really just automatically, yeah, it's implied. So yeah, I think this is maybe a little bit confusing. I'm not really storing anything here, right? Any other questions? So as you can see, the tag store in direct map is significantly smaller than the tag store in a fully associative. All right, so let's say I have an access pattern like this. I have address 0, then address 1, then address 2, then address 8. Okay, and as I said, let's assume that these are consecutive addresses in the memory, and each one is 1 byte, so we kind of store them separately. As you can see, the way this works is that I take the address 0, and let's say, if you remember, I told you that the addresses are 8 bits, right? So you've probably seen this before. So I'm gonna like divide this into 2 parts. You know, the tag and the index. Okay, and and then based on that, I'm gonna assign rows. So for example, the address 00 are gonna be mapped here. Address 001 gonna be mapped here. And then address 8 is going to be like this, right? So which means that, again, address 8 will also be mapped here, right? The difference between 8 and 1 is that the tag that I stored for 0 is 0. For 8, the tag that I'm going to store is 1, right? And the same story for 16 and 24 and so on and so forth, right? So what happens is that if this sequence of address comes, okay, what I'm going to store here is that I'm going to store 0 for this tag here. Then the address 1 comes. The address 1 is going to be mapped to index 1. But the tag still for address 1 is also 0, right? And I'm going to put valid bit here, valid bit here. There will be some data that will be stored there as well. I'm not going to show you the data. This is just the access pattern of the addresses. Then address 2 comes, and again, the tag will be 0, but the index would be 2, and then I'm going to store some data here. Okay? Then address 8 will come, and what we're going to see is that the address 8 will be mapped here. And since the tag doesn't match, I need to basically what we call evict. So I need to evict this and replace it with 1. Okay, so I'm going to store the tag 1 here and the new data here. All right, so this is what we call a cache miss. Okay, and 8 is not going to be stored there. Okay, at the first, but it's going to be updated and stored there. For fully associative, the way it works is that, remember that we don't have any index. So what we're going to store is that I'm going to store 0 here, I'm going to store 1 here, 2 here, and 8 here, okay? And then you do valid, 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 and then data, 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 whatever those data are, okay? So I'm not going to replace 0 with 8 because I have empty spaces. At some point, I'm going to run out of these empty spaces, and I need to decide where do I want to replace. For now, we haven't described that strategy yet. Soon, I'm going to describe that. For direct map, there is no decision. When the data comes, I need to replace it. But for fully associative, there's some decision that you can make because any row can be sitting anywhere they want, so we can decide who we want to evict. For direct map, you cannot decide. So does that make sense so far? Any questions? Great. So let's actually see another like little bit more problematic pattern. So let's see instead of like having 0, 1, 2, 3, 4 up to 8, let's say we have 0, 8, 0, 8, 0, 8. Okay? So for direct map, if you remember, I told you that at first we're gonna store store 0, but then this address 8 will come, and then I need to replace this with this one. Then the address 0 comes again, and unfortunately, although we had it before, we replace it with 1. So now I need to get rid of it and store it as 0. And as you will see, the story continues. So if I look at the patterns of this cache, I see that the first one, it's a miss because that's the first one we see this data. We never see it before. That's why it's always a miss. You can never do anything about that. This is what we call compulsory miss, because the first time you see a data, there's no way that you store it in the cache, so it's always a miss. The story of the cache is that if I see it again, do I remember it? That's what you want to have. The 8 is also same story. This is the first time you see it, and it's going to be a miss. You would expect that at this point, from this third axis, it will be hits, right? So you would, ideally you want to see a pattern like this, right? So you want to see 2 misses and then followed by lots of hits, because you keep seeing the same thing, so you should be able to capture this kind of behavior. Unfortunately, for direct map, for this particular case, that's not going to happen. You're going to continue seeing misses, 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 because essentially what you do is kind of flip-flopping, ping-ponging between these 2 addresses. But of course, if you look at the fully associative, we will see that I put 0 here, 8 comes, and I put it here, assuming that the cache is empty at the beginning, which means that the first 2 are going to be misses, but afterwards, exactly that's what you want to see, and that would be all hits. And then this story continues as long as you kind of do that. Okay? So it seems that the fully associative is a much better option in this case, in many cases. Okay? So let's actually compare the direct map and fully associative, because it's not always just the miss that the hit rate or the miss rate that is important. If you remember, there was also other 2 things, the miss penalty and the hit time, that was also important. And you see the average access time is kind of a combination of all this. So let's actually talk about this. Can someone tell me the hit time, if you want to compare the fully associative cache versus a direct map cache, which one has a lower hit time? Yeah. Between the direct map and fully associative, which one has a lower hit time? Direct map, right? Because it's very easy to know which one, what is where, right? So I have to, for let's say, for example, in this case above, for 8, I can just go here and see whether the data is here or not. But here I need to do at least 2 comparisons, right? And sometimes if I'm unlucky, I need to search all the way down. If the data is here, I need to do 8 comparisons, okay? So the hit time for direct map is actually much lower than for the associative. What about miss rate? Yeah. Doesn't matter. So direct map has, direct map has higher miss rate than fully associative. Why? Because I told you, just gave you an example. Generally, you utilize the space in your cache in direct map much less than a fully associative. Fully associative, it doesn't have any mapping. Everyone can go wherever they want. Versus in direct map, unfortunately, that's not the case. What about miss penalty? Yeah. It will be the same, right? Why? Exactly. So in both cases, when you have a miss, you have to go to a lower level. And then let's say that they have the exact same lower level, which is the case in all systems. It means that the miss penalty in both cases is exactly the same, okay? So miss penalty is not a function of the current design of the cache. It's a function of the next level of the cache, okay? So for example, if the next level is another direct map or fully associative, you have to then compute the miss penalty for that. But if I just look into one level of cache and comparing the two, that's what I'm going to get, okay? So if you look at this formula, you will see that in some cases, direct map is performing better, right? In some cases, fully associative is performing better. In some cases, they are the same. So which one is better in terms of average access time? So which one should I use? Anyone has any suggestions? If I give you an option of pick one, what would you do? Yes, exactly. So it would depend, right? So it would depend, first of all, based on this number. Like I'm telling you that this one is better than the other one, but they didn't tell you how much, right? And the second thing is that what do you want to get? If you are like getting the data quickly enough versus not. So let's table this kind of comparison between these two. I'm going to give you another option that is kind of between these two options, and then that's where you will see that where we're going to usually use. So in reality, we never use direct map or fully associative. Not never, rarely use either of those two. Instead, what we're going to do, so by the way, this is the what I just said. In reality, what we do is kind of using both. Okay? So how do we do both? The idea of do both is what we call set associative cache. Okay? Which what we call, we add associativity to our cache. Okay? So here's what we're going to do. Okay? So remember that I told you that direct map was this structure like this, that I have rows, I mapped everyone to each row, and fully associative was that there were no notion of a row. Everybody was the same row, okay? So the combination of those two would be something like this, okay? Then I'm going to add what we call ways or associativity to each row, okay? So I'm going to do it this way. I'm not going to say that, okay, it's free for all. I'm not going to also do uh, assign seat. What I'm going to do is that I'm going to divide it into sections, which we should call sets. So for example, let's say left, middle, and right. And then what I'm going to do is that, okay, on the left, you can choose wherever you want to sit. On the middle, you can choose wherever you want to sit. On the right, you can choose wherever you want to sit. But I'm going to categorize you. I'm going to say that like these groups can only sit on the left. These groups can only sit in the middle. These groups can only sit on the right, okay? So I'm going to have some level of indexing first, but then within those index, I'm going to have options of where you want to sit, okay? So instead of like, so what I'm going to have is that I'm going to have some index. So let's say instead of having, let's say, 2 bits of index, what I'm going to have is that I'm going to have just 1 bit of index, okay? So I'm going to have 2 different rows. We call this a set, okay? I'm going to have 2 different rows, but let's say I have 4 different areas that I can use. In that case, I'm going to assign 2 columns, which we call ways. This is the equivalent of what we had for fully associative. And I'm going to assign 2 to each of these rows or each of these 2 sets. Within this row, you can pick any one you want. Okay, so you can either sit on the left one or the right one. We call this way 0 or way 1. But across the rows, you cannot switch. Okay, so for example, in this particular example, I'm going to use the least significant bit as my index, which means that if your address is even, you're going to assign to row 0. If the address is odd, you're going to be assigned to row 1. But within that row, it doesn't matter the rest of the address. Whatever it is, you're going to use that. So essentially, what we're going to do is that 1 bit of index, the remaining going to be a tag. So this tag could be either stored here or stored here. Okay? So how do I search? The first thing I'm going to do is that I first select the index. But within that index, then I need to search within the whole set. Okay, so if I have 2, I need to check both. If I have 8, I check all 8. Okay, you had a question? Oh, so the question is, why are we using the lower bits for the index? Why not higher orders for index, right? So like, what's the strategy for the indexing? Uh, so for example, I could do, for example, use the most significant bit as the index and then the rest as the tag, right? So the structure doesn't change, the indexing change. Remember that I told you that I want to utilize locality, right? And remember I told you that there was temporal locality and spatial locality. Temporal locality doesn't matter which address I'm using. But spatial locality does, right? So for example, what I want to do is being able to distinguish between nearby addresses. If I use the most significant bit, then I cannot distinguish between address 0 and address 1 because their most significant bit is the same. So they're going to be mapped into the same line, which I don't like because remember that we had very likely that if I access 0, I'm going to soon access 1 and so on. So I don't want these to be conflicted. So that's why. So it's the same story, the reason that we use lower bits of PC for BTB, the exact same reason here. But good question. Can someone tell me the O notation for fully associative? Is it O of n? No, for set associative. So let's say I have, initially I had n lines. Now I have, let's say, k ways, and as a result, I have n divided by k lines. Right? So I have n divided by k lines, but then I have k ways in each one. Still, I have n separate units. So what would be the old notation for this? Yeah. Yes. So what will happen is that it will be O of k. Why? Because the rows I can quickly do it by 1, right? So I know exactly the index. So O of n for selecting the sets. But then within the set, I need to search through all possibilities, right? And if I have k rows, that would be O of k. Okay? Does anyone here doesn't know what is an O notation is actually? Okay, so everybody passed the course on algorithms. Great. So as you can see, now it's kind of like best of both worlds kind of thing, right? So remember that in set associative, in direct map, it was O of 1, and in fully associative, it was O of n, which was like a huge number. But now I can kind of control it. I can add more rows as I want, but if I make the k constant, the time for searching doesn't grow, right? And the nice thing about this is that then if the k is some decent number, then I can kind of like fix the conflicting issue as well, right? So for example, for the example that I gave you of 0808, right? All I need to do is that if k is bigger than 1, if I at least have 2 different columns, I can store both 0 and 8, right? And that would be all I need for a set associative cache. We call it set associative because so the rows, we call it set. Within each set, then I have associativity. Fully associative means that everything is associative. And direct map means that we are directly mapping. That's where the names come. Okay, so you have 3 different options. I can have fully associative, I have direct map, and I have somewhere in between, which is the set associative. And set associative is the model that we use in all modern caches, okay? So all of the modern systems using set associative. How many ways do we use? How many these columns do we use? Depends. Typically, we have 8 or 16, okay? We don't go beyond that because remember that if I increase k, my search time goes up. And I don't want that, okay? So usually, I stay within 8 or 16. I don't go beyond that. Sometimes even 4, okay? Less than 4, usually not helpful that much, okay? So it's better to actually go with direct map. So what happens is that in most systems, you have smaller set associative as your level 1, and then as you grow, you increase the associativity of your cache, okay? You rarely see fully associative or direct map, although, as I said, there are examples of real systems with that as well, okay? And as I said, some namings, we call these rows a set. And within each set, we have what we call way. So each column is called a way, okay? So for example, this is what we call a two-way set associative cache, okay? If I tell you that I have a cache that is four-way set associative, means that I have 4 ways per set, okay? So how does the cache lookup look like for a set associative? The cache lookup is similar to direct map, but now remember that I have multiple tag stores, right? I need to check them all together. So I have two options. Either I can do them one by one. So for example, let's say I have a two-way set associative. I can search the first one. If it's there, great. If it's not, I search the second one. The other option is that if I want to really get speed, I can search all of them at the same time. So I have parallelism not only for data versus tag, but also in my tag search, okay? So for example, if I have a design like this with a two-way, what I'm going to do is that I'm going to take tag 1, I'm going to take tag 2, I'm going to compare each one individually with the tag that I have, and then I'm going to OR them together, okay? So it's the tag either going to be here or none, right? This is the 3 possible options. So what is the trade-off here? Of course, the trade-off is that I need more circuitry and need more power because I need to search multiple of this at the same time. For example, for an 8-way set associative, I'm running 8 different comparisons at the same time. But the good thing about this is that this then makes the system as fast as a direct map cache because I can find them, since I've searched them in parallel, I find them within the same as if I'm just doing one search, okay? I cannot get it beyond one search, but if I have 8 parallel searches at the same time, then I'll have a cache as fast as a direct map cache. But this is actually kind of is as good as this fully associative cache. Then the trade-off, of course, is I need more space and I need more comparisons. But that's the kind of trade-offs that I'm willing to take, okay? And again, that's what happens in real systems. And as you can see, not only I have the parallel tag search, I need to also access the data from all of them, right? So you also access all the 8 data stores or 4 data stores or 8 data, whatever you have in parallel. And then depending on which one of this is a hit, you're going to select that. If none of them is a hit, you're going to just forward a miss, and you go and look into the next state or next level of your cache or memory or whatever you have, okay? Again, you can have this kind of pattern here. And as you can see, the difference between direct map and set associative is that in set associative, you still have indices, but the number of bits for an index is much less. The number of bits for the index is much less than what you have in direct map, okay? But on the other hand, the tag would be slightly bigger. And you have 2 of these guys, right? Versus what you have in a direct map. So again, you can compute the tag size, you can compute the number of bits for the index, and so on and so forth. In your homework, you're going to see that we're going to ask you for different designs. We're going to ask you to do that. If you look into the pattern that we had before, the 0808, if you remember for the direct map, it was miss and miss. And then, as I said, ideally, you would expect that from this point on, it will be all hits. For direct map, unfortunately, it was all misses. For fully associative, if you remember, it was all hits. And then if you look into the set associative, you will see that what will happen is that 0 going to be mapped here, and 8 going to be mapped here. In the same set, although their indices are the same, since I have now 2 available options, I'm going to use both. As a result, what's going to happen is that the first 2 are going to be a miss, but then the rest is going to be a hit, okay? So as you can see, my set associative is kind of like similar to my fully associative in terms of the patterns that it generates. Of course, this is just for one example, but on average, you get very close to a fully associative, okay? And yeah, this is a pattern. This is one problem for you guys to look into it. I recommend you to do that. I'm not going to do it now, but if someone wants to do it and post it on campus where that would be great. Let me actually do this and then give you some time for a break. Let's actually revisit this hit time, miss penalty, and miss rate. So who wants to compare the three together for hit time? Yeah. Mm-hmm. Well, a miss rate. Yeah. Yeah, so it would be this way. So fully associative would be the best, and then set associative. Well, a miss penalty, the same, right? So it's, as I told you, it doesn't matter what you use. Okay? But also one thing I want to say is that the fact of closeness, so what happens is that set associative and direct map would be very close, but fully associative would be very far away. In terms of miss rate is also like this, okay? So this is what you're gonna get, okay? So you're gonna have, in terms of hit time, direct map is still kind of the fastest, but set associative is almost close, especially if you have the parallel search, it's almost identical with direct map. But fully associative is very, very far, okay? Miss rate, direct map would be the worst. Sense associative would be very close to fully associative. Still, fully associative would be the best because you have you can utilize the entire cache, versus the set associative you can only utilize each set more efficiently. Okay? And as I said, miss penalty doesn't matter. All right? Let's have a break and then we can start talking about other things, especially for the set associative and fully associative. Okay? Great. Let's continue. All right, we're recording, we're good. All right, so let's start talking about, so now we know the mapping. We know that there exists three different types of mapping: direct map, fully associative, set associative. So let's actually talk about the data management, right? So what should we do uh, when there's no longer space in the cache? Because so far I told you that address comes, everything is invalid, you put it here, we put it there, great, things works, okay? So what should we do if the cache is full? So going back to the examples that I have before, let's actually add a little bit more to it. So let's say I have a direct map and a fully associative cache. And let's say the patterns I'm going to see is going to be like this, okay? So I already told you that you need to basically break down the address. So for example, same thing. So 8 rows, 8-bit address, so on and so forth. So if I break down the address, I'm going to see that the indexes would be 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on and so forth, until we reach to the 8 so for 7 it's going to be 1, 1, 1, and for 8 it's going to be a 0, 0 again, which means that these two guys are going to map into the same, and the rest going to be mapped into the difference. In this case, the tag for all of these guys would be 0 until we get to this one that the tag would be 1. So this is just a simple mapping. So what's going to happen is that I'm going to see 0 to 7, and what will happen is that I'm going to basically store tag 0 in all cases and change all of these guys to 1. And then I'm going to have some data here. Then 8 comes, okay? And for direct map, as I told you, we're going to check the index. We see that the index is 0, 0. What we're going to do is that we're going to check the tag. We'll see that the tag is supposed to be 1, but it's 0. So what we're going to do, excuse me, is that I'm going to get rid of this. I'm going to what we call evict this cache and replace it with this one. For direct map, so it's very straightforward, okay? But if you look into the fully associative, now we don't have index anymore. So essentially, I'm going to store the tags here, right? 0, 1, 2, all the way to 7. Or you can show it with like the binary. It's going to be 1, 1, 1. Doesn't matter. But then 8 comes, okay? So now I stored 8 things from 0 to 7 in my cache, and its cache is full, and everything is valid, okay? Now 8 comes, and the tag of 8 is, of course, 8. It doesn't match with any of these. So I need to replace and store this in the cache. The first question is, you might ask that, do I even need to store 8? Maybe I just happy with what I have, and I don't store 8 at all. That's one strategy. But for now, we're going to talk about that later, that whether or not we want to store 8 at all in our cache. But let's say we want to. So I need to pick a candidate and evict, okay? What should be that policy? Who should I select? For direct map, I don't have the option because I just go by index. But for fully associative, since all the 8 lines are equal, I can select any of them and send it out. So let's talk about those strategies. What do you think should be the strategy that we're following here? Give me suggestions. You pick the oldest one, and then how do you define old? So if you need to kind of keep track of time, right? So you need to kind of keep track of where each line came, and then somehow you pick the oldest one. Okay. Any other suggestions? Yeah. Least recently used one. So you kind of keep track of the usage, not the time, right? And if you keep track of the usage and say that, okay, which one was the last time that we used this? And then I'm going to kick out the one that is the latest, the least, the oldest in terms of usage. Any other suggestions? Mm-hmm. So it's some form of a pointer, but then keep in mind that your patterns could be irregular. So the pattern is not going to be 0, 1, 2, 3, 3. Sometimes it would be 3, 4, 7, 2, 1, 7, 4, right? So it's not going to be circular in the sense that, yeah, you have this nicely like incremental addresses and goes back and then you go circular. The addresses could come from many, many different places. So don't bank on the fact that things are right after another. It could be very irregular patterns. Any other suggestions? Well, yeah, good thinking. Yeah.
I think that's the same problems that's most oldest has.
Mm-hmm.
Yeah.
So least frequently, so we kind of have a counter-based approach where we count how many times I've used things, and then the one that is not being used that much, then I'm going to get rid of that. So the recently versus least frequently, the difference is recently is more of a notion of time, frequently is notion of the numbers. Mm-hmm. Yeah, that's also, yeah.
Then you kind of, once you look for a space,
Mm-hmm.
then you replace it, and you set data 0
Mm-hmm. Yep. So that's basically suggestion of one thing that we're gonna actually discuss. Yes. So the comment was about like making some form of at least recently used, but not fully recently used. Some simpler version. Yeah. There's also very simple solutions for this. Anyone wants to give that? Yeah. Yeah, you pick random, right? Like you get rid of one of them and you move forward. You can do FIFO, you can do LIFO, like all those things, right? At least last in, first out, first in, first out, random. So you can do those things as well, okay? So why is it important that? Why does it matter that which one should be used? And why should we pay attention and care and find the one that's really good? The reason for this is this, right? So I'm going to have a pattern like this, and 8 will come, okay? And now I need to decide. So if I decide, for example, to get rid of 0 and replace 0 with 8, versus if I decide to, let's say, for some reason, decide to get rid of 7 and replace it with 8. The difference between them is in future accesses. So for example, if in near future you're going to have something like 7, or you're going to have lots of 7s, if I get rid of 7, then I'm going to have a miss. If I get rid of 0, I'm going to have a hit, right? So if I have this hindsight, if I had this knowledge of the future, what we call the replacement policy, the policy that we use for replacement, could directly impact the behavior of my cache and the performance of my cache. And what you want to do is that hopefully you can come up with the replacement policy that service your future the best, right? So essentially what you're really trying to do is that anticipating or predicting what is going to be the most likely thing that's going to be used in near future. You want to keep that, and you want to get rid of the rest, right? So that's why, for example, you do least recently used, which the idea would be that the ones that's not being used, it's likely that it's not going to be also used in near future. Or you're going to do least frequently used. So you're basically saying that these guys has the track record of being used a lot, but this particular block has not been used that much, and it's very unlikely that it's going to be used in future as well, right? And then if you kind of have no idea which one, then maybe you should do randoms, because at least random doesn't give you any biases toward any of these, right? So there are different strategy and school of thoughts for this. And we're going to go over a few of them. And there are many other as well that we're not going to cover, okay? And then, as I said, so this issue exists in fully associative, but does not exist in direct map, right? As I said, direct map, you don't have a choice. So your life is very easy. You don't even get to pick. Set associative, though, is kind of somewhere in between, right? So in set associative, if I see something like this, you will see that 0 goes here, 1 goes here, 2 goes here, 3 goes here. 4 and 0 now are mapped together. So 0 goes here, 1, 5, 6, and 7, right? And now 8 comes. And 8 also maps to 4 and 1. So what will happen is that in a set associative, we kind of have somewhere in between again, right? So I need to kick out something from this index 0. I cannot kick out evict things from index 1 or index 2. I have only 2 options. But I still I have an option. So I can choose whether I want to get rid of 0 or get rid of 4. Okay? So keep in mind that, so set associative, still you have somewhat an option, depending on how many ways you have. For example, in this particular case, what you do with 8 has nothing to do with 7, because 7 and 8 are mapped into 2 different addresses. But if, for example, we have addresses like 4 and 0 coming in near future, then what you do does matter. So set associative is still, replacement policy is important, but let's say somewhat less important than a fully associative. Okay? So let's focus on this, that what to evict when we have a fully associative or a set associative cache. And as I said, direct map doesn't have this problem. As I said, the first thing is that you pick at random. The good thing about this is that it's very easy to implement, because you don't need to store any sort of metadata. You don't need to remember or keep track and all that. But the negative thing about the random is that you're not use this smartly enough. It means that you're not really using or utilizing the fact that we're going to have locality. Remember, the main thing in the cache is that we're going to have what we call temporal locality, which means that if I use something, it is likely that in near future I'm going to use it again. And random doesn't understand that, unfortunately. Okay? So the trade-off is that easy to use, much less overhead in terms of implementation, in terms of runtime, but maybe not the best performance. So what we do instead, and this is again what has been implemented in many modern systems, is what we call the LRU policy, least recently used policy, okay? Why least recently used and not least frequently used? The reason is, again, temporal locality. That think about this is that things get kind of like outdated after a while, okay? So among the options that I have, the idea of least recently used is that given temporal locality, given this statement that something that's been used is very likely to be used in near future, between the 8 options, for example, in this case, I'm going to pick the one that's been the oldest in terms of usage. I'm going to get rid of that because it's much less likely. It's not 0, so keep in mind that I cannot achieve 100% accuracy, but at least I can get closer to that based on this. And then you might ask, okay, what will happen if that temporal locality does not exist and it's not like a law? So in that case, your least recently used policy is not doing well. Okay, so it's not like least recently used is the answer to everything. That's why there exists other methods that we're not going to cover. All right, so good thing about least recently used or LRU is that you are really, really exploiting and extracting the locality, especially the temporal locality. The downside, though, is that now you need to keep track of this, right? You need to keep track of recently used. How do you know which one is which, right? So for example, if I have 8 different rows, let's say this is a fully associative cache, or it could be a set associated with 8 different ways. Not only I need to store the tag and data, now I need another column that basically tells me when was the when was the last time I used this. So I need to either store some form of a timestamp or something, some form of an order or something like that to tell me who was the least recently used. Okay? And then I need to kind of pick the top candidate and get rid of that. Okay? So obviously the downside would be that now I need to an additional storage for each single line in my cache that comes with overhead. Okay? So let's actually, but as I said, this is what we're going after because the balance between what we gain from the using at least recently used versus let's say using just a random or FIFO is that we're gonna extract the locality and that helps us with performance. That's why we are willing to pay this extra penalty. Okay? So let's say how this works. So essentially the way this works is that I'm going to add an additional column in my cache, and usually this goes into my tag store. And that's what we call usually a position, okay? You can show it with P or different numbers. The position, it basically tells, it's an ordered list that basically indicates the order of of each line in terms of usage. And then the way it works is that, for example, if I have 7, 8 of these, the higher the number, it means that more recently it's been used. Okay, so 7 means that this was the very last line in this set that has been used. And 0 means that it's been the oldest. So it was the least recently. So if I want to kick something out, I'll go and find the position 0, and I replace it with the new data. Okay? So if I have patterns like this, okay? So if I have a pattern like this is going to be the way that I'm going to, let me see if I have it here. Yeah. If I have a pattern like this, here's what I'm going to do. Let's say, for example, initially, I'm giving you a random initialization, but this is kind of like I'm showing you a snapshot. Let's say, for example, the positions are actually like this, okay? Positions are 0, 1, 2, 3, 4, 5, 6, and 7. Doesn't need to be like this. I'm just giving you an initial number, okay? So now let's say 1 comes, okay? So 1 is already in the cache. Great. That would be a hit, okay? And now I need to decide whether I want to promote this because now my access to line 1 is now the most recently used, or MRU, okay? So what I should do is that I need to update the position of 1 to the most recently used position, which is 7, okay? So what I'm going to do is that I'm going to change the position of this to 7. Since now I kind of moved 1 to 7, I need to also update the rest, right? Because I cannot have two 7s. So what I need to do is that update everybody else. So what used to be 7 now 6, what used to be 6 is now 5, and so on and so forth. So this is 3, this is 2, this is 1, and this was 0. Since this was before 1, you don't need to update that. So this would be 0, okay? So this will be the updated position of my cache. So if I look into this, I will see that the most recently used, or MRU, is line number 1. The least recently used is line number 0. And there's everything in between, okay? Then 2 comes, and same story, it will be a hit. And now I need to update again. And this time I need to basically do, so now this guy goes to 7. Now this has to be 6. This has to be 5, 4, 3, 2, 1, and 0. Okay? Now 8 comes, and as you can see, 8 is not been stored here. So it will be a miss. But I need to now evict something. What should I evict? I'll go and find the one that is showing 0. In this case, it's 0. So I'm going to evict this one. I'm going to change the tag to 1 because the tag of 8 is 1. And then the next thing I'm going to do is that since this is the one that I replace the cache with, I need to also promote this to the MRU. So not only I replace this, but I'm going to promote this. So I'm going to put this as the new 7, which means that everybody else now needs to be updated, okay? So 1, 2, 3, 4, which means that now the least recently used line is this line, is line number 3, that with the tag 3. So for example, now that 9 comes, okay, this will be also a miss, but what I'm going to evict is this line, okay? And what I'm going to do is that, again, I'm going to replace this with tag, again, equal to 1. Sorry, equal to 9, and sorry, this tag was 8 because it's a fully associative. And then I'm going to put this as 7, and then at 6, and then this would be 4, and this would be 5. And now this will be 0, and this would be 1, and this would be 2, and this would be 3. Okay? And then the story continues, right? So we're going to keep repeating this process over and over again. When it's an access, we're going to promote that line, whether or not it's a hit or miss, to the MRU position. And then the rest will be updated accordingly. So I need to also change that in the system as well. Okay? Any questions about the LRU policy? Okay. So how many bits do I need to add to each position for each row? Anyone? How many bits? Yeah. Yeah, 3. So essentially the log of number of rows, right? So whatever I need for how many rows that I have, log 2 of that is the bit that I'm adding to every single row. So it would be row times the log 2 of row. That's the number of bits that I need to add. So this is the kind of the area storage overhead of this system, right? So that's great. Keep in mind that this typically means that it's a lot of overhead if this number of rows is huge, right? So for example, imagine a system with thousands of rows for a fully associative, or let's say 16 different columns for a 16-way set associative. I need to store a lot of bits, which might not be the best option, okay? So that's why there are some solutions to make this a little bit more cost effective. This goes into what we call the pseudo LRU or PLRU. So there are multiple ways of creating pseudo LRUs, and in fact, pseudo LRU is the one that's actually implemented in real hardware, because in real hardware, LRU, although it's working well, it's a little bit more it's the area overhead and the power overhead is really bit large. So instead we're trying to kind of approximate LRU. So that's why we have pseudo LRU. Okay. The one I'm going to talk about is called NRU, or not recently used. But there's also another one that is based on tree LRU. So it's called tree PLRU. The one I'm showing you is called NPLRU, so not recently used, okay? So let's see how it works. So what I'm going to do is actually, someone already explained the method, but I'm going to do it again. So here's what I'm going to do. Instead of having positions, I'm going to just add one bit, okay? So I'm going to call it a flag. You can still call it a position, but I'm calling it the flag because it's just one bit. Some books and some resources call it the used bit or NRU bits, not recently used bit, okay? So here's what I'm going to do. I'm going to start with like all zeros flag. And the algorithm that I'm going to follow is this, that if the line is used, I'm going to I'm going to change the flag to 1. Okay? So if a flag is 1, it means that it has been recently used. Somewhere in this window. But it's only 1 bit, so it means that there are multiple of them that might be 1 bit. But then what will happen is that if all of them becomes 1, okay? Sorry, the first thing I'm going to do is that if it's being used, I'm going to select bit 1, okay? Now if I want to replace, I'm going to find the first 0, okay? And I'm going to kick that out and replace it with the new data. The reason for this is that if the flag bit was 0, it means that it hasn't been used recently, okay? If the flag is 1, it means that it has been used recently. So I want to kind of like prioritize those that's been used versus those that hasn't been used, okay? So that's what I'm going to do. So essentially, I'm going to start with all zeros, but then when I have a data that is in the cache, on a hit, I'm going to set the bit to 1. So let's say, for example, address 1 comes, and what I'm going to do is that the address is there, let's say, so it's going to be a hit. But what I'm going to do is that I'm going to change the flag from 0 to 1. Okay? So on a hit, I'm going to update the flag to 1. Okay? Then I'm going to continue on a miss. So let's say, for example, address 9 comes. On a miss, what I'm going to do is that I'm going to the first row that its flag bit is equal to 0, and I'm going to replace that with 1. We replace that with the new data, okay? So for example, let's say my flags are something like this. It's like 1, 1, 0, 1, 1, so on and so forth. What I'm going to do is that I'm going to start from the top. So I'm going to start from the top. Always I'm going to start from the top. And I'm going to find the first line that the flag is equal to 0, okay? If there are multiple options, so for example, there is 0 here, there is also 0 here, as I said, it depends on my search. Typically, I start from one direction, which means that I start from the top. So in that case, I always prioritize kicking this out versus this out. There might be opportunities for further optimizing this, which we usually don't implement it in NRU because we want to keep it simple. So we're going to start from one direction, always go down, first find the first one, replace it, okay? So that's as easy as this. So now I don't need to do anything about the rest, okay? There's only one thing that I need to be worried about, and that's when all of these guys becomes 1. Because if all of them are 1, then if the new line comes, there's nothing to replace this with, okay? So if all of the flags becomes 1, I'm going to reset all of them, okay? So if at the moment that all of them becomes 1, I'm going to reset all of them to 0. Okay? In that case, it kind of like if all of them becomes 1, I pick at random in sense, right? Uh, and that's kind of the idea that we are following. So it's not going to be as great as the least recently used, but it's fairly close to an LRU. And there has been research and experiments and so on that shows that this is actually up to 90% or even more in terms of accuracy when compared to LRU. Okay, but the beauty of this is that it's only 1 bit versus multiple bits that you need for the counter. You get rid of the updating things, all those things. So it's very good in terms of area efficiency. Okay, so this kind of like this is the summary. So you start from all zeros. On a hit, you set bit to 1. On a miss, you find the first row, usually starting from the top, and then you put the new data there. Um, and then if all bits becomes 1, you reset and then pick the row that's, again, the first row or whatever row that's there. Another thing to remember is that when I install, okay, so for example, here on a miss, let's say this one was 0, this one is also 0, and address 9 comes. So I'm going to search through the cache, and I'm going to say that, okay, this guy, I can replace it, okay? So I put 9 here, and I usually set the flag to 1 as well, okay? So if the new line comes, not only I replace it, I also set the flag to 1. There's different ways of doing this. We typically, there has been other implementations that set the flag to 0. There are some cases that set the flag to 1. If we ask you some questions, we're going to tell you what you should do, whether you should set the flag to 0 or set the flag to 1. Okay? Questions? Great. So this is kind of like what we call a replacement policy. So the things that I've showed you so far was the replacement policy. And if you pay attention, there was like 3 things that we need to pay attention in replacement policy. It's called install, update, and replace, right? So install means that where should I put the new line? Update means that what should I do on the hit? And then replace means that if the cache is full, what should I replace the new data with, right? So you can see that, for example, for random versus LRU versus pseudo LRU versus other things that exist, there are different ways of doing this. Okay. And again, it would be a good practice for you to think about LRU, random, PLRU in terms of these 3 questions, and make sure that you understand what we exactly do for each different case. If you didn't, maybe a good time to go back and revisit the lecture. Okay? Questions here? Perfect. So the question is, can we do better? Is this like PLRU is the latest and greatest? Is there other options that we can do? The answer is obviously no. There are many, many other things that you can do. Of course, anything that you do, there are trade-offs. So you can have better mechanism for approximations. You can combine pseudo LRU with some other methods. Another thing that you can have is some form of an adaptive strategy that you decide and make changes to your, let's say, update strategy or your reset strategy based on the workload or based on the current patterns. For example, one thing that many system does is that they look at their current miss rate. If they see that the miss rate is going up, then they change the strategy. If the miss rate is going down, then they keep their strategy. So you think about it as there's some form of a sensor in the system that can measure the miss rate and then change the strategy adaptively. Another thing that many system has is that they have multiple different strategies, and they kind of decide based on their performance, okay? So they say that, okay, this is strategy number 1, this is strategy number 2. In the last 10,000 cycles, for example, strategy number 1 was much better than strategy number 2. So from the next 10,000 cycles, I'm going to just use the strategy number 1, something like that. So there are actually ways of doing this. And also keep in mind that whether or not this is a good replacement policy is really, really dependent on the workload. We have different workloads. There are workloads that are LRU friendly, which means that they have lots of temporal locality. We have other workloads that are not temporal locality. They're not LRU friendly. So think about something like matrix multiplication, which what it does is just goes through the lines one by one and never repeats. If it never repeats, then your LRU would be terrible, right? Your graph applications, for example, like, if you visit nodes and you never come back and revisit nodes, it's not going to be great. So for many like graphic-based applications, LRU not going to be a good option. So there needs to be other methods. We're not going to cover the rest in this class, but again, it's one of those things that we're going to cover in a more advanced class. So if you're interested, either read it in your own time or consider taking other classes to read about that. Okay? And as you can see, the importance of the replacement policy is going to be on your miss rate. Okay? Replacement policy is not going to change your hit time, right? But it's going to significantly impact your miss rate, right? And it's also not going to change your miss penalty. The only thing that the good replacement policy can do is your miss rate. You have to be very careful not to touch hit time because your miss penalty, your replacement policy should basically happen what we call in the background, not in the critical path. So your search still has to happen similarly as before. You only update your positions or check things in the background when you want to evict. That's why your hit time is not going to be impacted. Okay? One last thing I want to say before I let you guys go is you have to also consider different types of misses. I kind of said this already, but let's actually make it more formalized. So we have 3 types of misses. We have one miss called compulsory miss. Okay? The compulsory miss means that regardless of what you have, how large is your cache, what the strategy you're going to have, you're always going to have the first time you see the data, you're going to have a miss because the data is stored in memory. It has to be brought to the cache for the first time. So it doesn't matter what you do, you're always going to have this compulsory miss the first time. And as I said, if your data is only been visited one time and one time only, all the misses you're going to have is what we call compulsory misses. And unfortunately, it doesn't matter what you do with your replacement policy, the size of the cache, nothing going to help you. There's one thing that's going to help you, and that's called prefetching that we're going to talk about it next time. Okay? Then we're going to have what we call a capacity miss. The capacity miss is for when we have limited capacity of a cache. That is basically we define it as if I had a fully associative cache, and it still had a miss, I'm calling this a capacity miss. It means that just because my cache was small, I couldn't store these values, okay? And then lastly, we have what we call a conflict miss. And this is a miss that happens only in direct mapped or set associative because that's where you're going to potentially have a conflict. So conflict is the type of misses that if you had a fully associative, you had a hit. But since you don't, you have a miss, okay? So the difference between capacity and conflict is that in capacity, it doesn't matter which of these 3 types of caches you have. You're going to always have a miss because of the storage size. The conflict is the one that's because you have direct map or fully set associative, you have a miss. Okay? All right. So we're going to pause here. In the next lecture, we're going to talk about further optimizations of these things. Some of it we already talked about, but we're going to go through every single metric, the hit rate, miss rate, and miss penalty. I'm going to give you optimizations. These are kind of modern techniques that we use to optimize this further. Okay? All right, guys. See you next week.